All right, this is going to be the algebra section 4 on quadratic functions. So if you remember, we left off with linear regression. Okay, so let's look at some new data. Okay, and let's see if we can see the difference between what makes a linear function and what makes a quadratic function. Okay, so if we consider this data, here are the years since 2000. 0, 1, 2, 3, 4, 5, 6, and then the price in dollars is this. And if we notice, what do we see? The price went up by 2, up by 2, up by 2, up by 2. So that change, we would think this would be 13, right? So what patterns do you see in this collected data? Looks like it's going to go up by 2. Okay, and if we're talking about dollars, I guess I would say up by $2. Okay, so are these linear related? Okay, I would say yes, because there is a constant rate of change. Okay, so write a price function for this. So if you remember, our equation is y equals mx plus b. Okay, so in this case, what is it? I guess I'm going to say write a price function. So I'm going to say p of x, where p is my price, x is my years since 2000. So what are we going to do here? My slope is 2, right? That's my constant rate of change. Okay, and then how do I find my y-intercept? Well, again, it's when x equals 0, so I think it's just 2x plus 1. Okay, so that's pretty good. If we plot this data, we should be able to get a nice graph. I don't know, this is awfully big here. So here's 0, 1, 1, 3. So here's 1, 1, 2, 3. Here's 2. Hopefully you can see this. 1, 2, 3, 4, 5. That'd be at 5. So let's see, up 2 over 1. Up 2 over 1. It's going to be easier for me to just kind of stay within my line here. So I get my function that looks something like that. Okay, so we should see that we get a line. That's the type of graph, because this is linear. Okay, so not too bad. All right, well, what next? Let's look at this table. Okay, here it goes from 1 to 2, 2 to 5, 10 to 17, and then up to 26. So it's certainly not, if I look at my difference here, it's 1, here it's 3, here it's 5, here it's 7, here it's 9. So it's certainly not a constant rate of change, but if I notice this, my second degree is constant. Okay, so that leads me to believe that this is not linear. Okay, because it's not a constant change. Okay, so fill in the box. What do we think? 1, 2, 5, 10, 17, 26. So up by 1, up by 3, up by 5, up by 7, up by 9, up by 11. So I think that's going to be a 37. Okay. So if we plot these, what do we get? Well, here's 0, 1, 1 and 2, 1 and 2. I'm going to skip to 4 and 17. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So kind of labeling some of these. Okay. So let's see. 2 and 5. Here's 2, 5, 3 and 10 is here. 4 and 17 is going to be, here's 4, 16, 17. 6 and 37. So let's see. 1, 2, 3, 4, 5. There's 25. 1, 2, 3, 4, 5. There's 30. So I can't do this point, so I'll do 5 and 26. 1, 2, 3, 4, 5. And 26. Okay. So it certainly doesn't look linear. I don't think I can draw a straight line through these and touch, right? that doesn't work, that doesn't work. So it looks like this has a little bit of a curve to it. I even missed that point. Okay, what type of graph do you get? Well, I don't really know because we technically don't know what this is. Okay, but I'm going to say not linear. Okay, it's definitely got a curve to it. All right, so the data in example 1 can be modeled as a linear function. Okay, and we saw many examples of that in the last sections. We talked about the first 3. Okay, all right, the data in example 2 can be modeled on what we call a quadratic function. Okay, a quadratic function, a function whose equation can be written and put into the form ax squared plus bx plus c, where a is not equal to 0, because if a were 0, then that would go away and we'd have a linear. We'd have bx plus c. So you can see we're just raising this degree, okay, to the second power. So which of these is quadratic? Well, this is quadratic. A is 3, b is 2, and c is 3. Okay, this is quadratic. A is 2. There is no bx, so b can be 0. That's okay. And c is -4. Okay, and I don't believe this is because this exponent is not a 1. So this is not quadratic. Okay, all right, and we should be able to plug in some values here. Okay, so if I'm given this function, -2x squared plus 2x minus 1, find the following. So when I plug in -3, be careful. The opposite of -3 squared is going to be different than -3 squared. Okay, so I'm putting parentheses around all of this stuff. -3 squared is 9. The opposite of that is -9 plus a -6 minus 1. So when I plug in a -3, f of -3 becomes -15 minus 1 is -16. F of 2 is 2 squared plus 2 times 2 minus 1. So I get -4 plus 4 minus 1. That becomes a -1. Okay? So be careful. I also want to kind of show you, if you have not done this on your calculator, if you go into y equals, you can plug in this -x squared. And again, be careful. The negative sign is different than the minus sign. So it's -x squared plus 2x. Oops, I'm up in my exponent. So this is -x squared. You got to come out of my exponent. Plus 2x minus 1. So hopefully we can see that. Okay. I'm just going to go set up my table. So I go second window. I'm going to start at 0 and I'm going to go by 1s. And I'm going to change this back to auto. So that should be my table setup above my window. Then if I go second table, I should see a nice table. Let's see. Here's my 2, -1 right here. My -3 is over here. That's the -16. That's what I got. Okay. All right. So, again, I like to show you that because as we do these things, it's going to be easier for me to use a table here. Okay. So given this following function, f of x equals x squared, okay, explain why this is quadratic. Well, it's to the second power. A equals 1, b is 0, and c is 0. So coming back up here, b can be 0 and c can be 0. We can't let a be 0. So that's why this is quadratic. So if I want to do a table, again, you can do this by hand, but why bother? Here I have x squared. I'm going to set up my table to start at -3 and go by 1, which I already have. And then I'm just going to hit second. And then here. So -3, again, you can do this by hand. -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. Okay, so pretty easy to graph this. At -3, I'm up here at 9. At -2, I'm out here at 4. At -1, I'm at +1. At 0, I'm at 0. 1, 1, 2, 4, 0.39. So we kind of get the feel right away for what these quadratic functions are. Quadratic functions are going to be what we call a parabola. Okay. Okay. It's U-shaped. Okay. So that's always going to be my quadratics. Okay. If I hit on my calculator, zoom 6, that's a standard window, we get a nice graph right away of that zoom 6. So there's my quadratic. All right. All right. So definition of a parabola. Okay. The graph of a quadratic function. Some of them open up, some of them open down. Okay. You'll learn how we switch those. Okay. And they all have this line here that's called the axis of symmetry. Okay. So I guess I'm getting ahead of myself. That's down here. Okay. They also have this point where it kind of changes direction. If you look at this parabola, it's coming down here. We get to that point, and then it changes direction. That is called the vertex. Okay. So if a parabola opens up, okay, that's if the x squared term is positive, then the y value of the vertex is going to be what? So if it opens up like this is a minimum. Okay. If the a part of a quadratic function is negative, then it's going to open down, like this one. And then what do we have? It's not a minimum. That becomes our maximum. And we call that point the vertex. Okay. It's the point where it's the turning point, the point where it changes direction. Okay. And if we look at these things long enough, hopefully we can see that they are symmetric. If we folded them in half, we'd get the same thing. And we call that line the axis of symmetry. Okay. All right, so let's take a little closer look at one of these. Use the graph below to fill in the blanks. So here's a quadratic function that is opening down. I don't know if you can see these points or not, but this is the point 2,5. This is the point 4,3. And this is the point 6, -3. Okay. So f of 4 is what? If I plug in a 4, what do I get out? I get out a 3. If I plug in a 2, f of 2, what do I get out? F of 2 is 5. Okay. What value for x can I plug in to get out a -3? Well, I think there's two of them. If I look over here, there's two values. F of -2, so the input could be -2, or f of 6 is -3. Okay? So if we have a graph, again, we should be able to tell inputs and outputs. What is the y-intercept? Well, here's the y-intercept. Your y-intercept is when x is 0, you get out a 3. Where is the vertex? That's my turning point. That's up here at 2, 5. Okay? So I can look at that from a table. Here's from a graph. If I look at the next one, that's a table. Okay? How can you tell by looking at this that this represents a function of x? Okay? Because for each one input, it maps to one output. Okay? So that's how I know it's a function. It's a mapping. One input goes to one output. Okay, so what's f of 4? Well, f of 4 looks like it's 3. What's f of 2? F of 2 looks like it's 3. And that's okay, it's still a function, even though those are the same thing. I didn't have a choice when I had these. Okay, where do I get out 19? Well, again, it looks like there's two places where my output is 19. This is my output. Okay, one of them is at 0, and the other one is at 6. What's the y-intercept? Well, the y-intercept is when x equals 0, so that is the point 0, 19. Okay? All right. So, we're going to be looking at a lot of different functions, okay? Quadratic functions are really the only functions that have this turning point, at least in the functions that we're going to be looking at, okay? All right. So how about this? Using a quadratic function to make a prediction. So here, what do we have? 1990, 95, 2000, 2005, 2010. 0, 5, 10, 15, 20. And it looks like these are my data points. So what's the next one here? It looks like the year is going up by 5. So that would be 2015. So this would be a 25. Let's see if we can't see what's going on here. This looks like it's going up by 0.9. Okay, right? This looks like it's going up by 0.6. Or no, 1.6. 2.2. And then 7.5. 7.5 minus 4.7 is 2.8. 11.4 minus 7.5 is 3.9. Okay. So here, I don't know what's the difference here. 0.7. 2.8 minus that is 1.2. This is 1.1. I don't know if I like that. 0.9. 3.1 minus 2.2 is 0.9. That is definitely 1.6. I think that was supposed to be a 4.2. Because then that would have been made that by 11. That would have made that by 13. Okay. Let me see what 2.2, 3.1, 4.7, 7.5, 11.6. Okay. So I don't think it fits. So it's not exactly quadratic. Okay. But we learned last time how to find the line of best fit. Okay. So now I'm going to try to find a quadratic that fits. Okay. So let's go into stat edit. And in L1, I'm going to put the year since 1990. Now, I'm not going to put in this bottom one because I don't know what it is. Okay, 15 and then 20. Over here, I'm going to put in 2.2, 3.1, 4.7, 7.5, and then 11.4. Okay, so you see what I'm doing here? I try to see, is it linear? And it certainly doesn't look like it's linear. The second one tried to match up, so I don't know if it's going to fit a quadratic. We're gonna find out here in a minute. Okay, so I put these in as L1 and L2. Okay, and then I'm going to run stat calculate, but instead of running linear regression, I'm going to run quadratic regression. I have them in as L1 and L2, and then I'm going to calculate. Okay, and notice here, it gives me an A, B, and a C. Okay? And then there's a note here that says an R squared value close to 1 means it's a good fit. And we got 0.9996. Okay? So again, we didn't talk much about that in the last section, but that's that R value we want close to 1. If you didn't get that, you need to go back and watch my last video, because that tells you how to put your calculator into diagnostic mode, and then that'll show up. So right at the end of section 4.3 video, I tell you how to get that value. All right. So we run this regression, and what do we get? Looks like I'm getting y equals, it doesn't tell me, 3 decimal places, so I'm going to get 0.021 x squared plus 0.045x plus 2.249. Okay, those are the values I'm taking right from my calculator. Okay. All right. So now I want to use this equation, okay, in part A. Okay, so I'm using this equation. to predict when the bottled water consumption will reach 20 billion. So to do that, I'm going to do two things. In Y1, I'm going to plug in this function. And in Y2, I'm going to plug in a 20. Okay? So in Y1, I'm going to plug in this function I just created, 0.021 x squared plus 0.045 x plus 2.249. And then in Y2, I'm going to put 20. Okay? Now, I can't use a standard window because my window right now, Y is only going up to 10. Okay? So I need to change this. I'm going to change it. I'm going to make Y go, well, I guess they're telling me how to do my window. Okay? So let me do my window. X is the years since 1990 is 0, so I'm going to go 0, and I'll go out for 40 years. So that'll take me out to the year 2030 if I add 40 to that, right? Okay, I want to go up to at least 20 billion, so I'm going to make this a 30 on Y maximum. And I should change my scales too. If I'm going from 0 to 40, probably 5 is a good scale for both of these. Okay, and now I'm just going to hit graph. And there's my parabola. So there's this first set of data. And then there's my Y equals 20. So there's my point of intersection. So hopefully you can see that. Okay. All right. So how do I find that point of intersection? So again, what we're really doing here is solving this quadratic equation. Where does this equal 20? So here's the blue line, that's this equation. The red line is just equaling 20. So my point of intersection is right here. And if I hit second trace, that's my calculate. What am I trying to find? Well, I'm trying to find my point of intersection. Okay, now my calculator isn't very smart. I can look right here and say, well, there's my point of intersection, but my calculator doesn't know that. So it's asking me which curve. So the first curve is my blue line. That's my equation. Just hit enter and it marks it. Then it jumps up to the second one. Just hit enter and it marks it. You can really make any guess, but just get in the habit of kind of getting close. That'll speed things up a little bit. And you can see without too much problems, I'm getting X is 28.022. 28.022. Okay. So using my graph, when will this be 20 million? Okay, so when will this get to 20 million? It'll be in 28 years roughly. Okay? So, a couple things going on in this page. We're using quadratic regression to find an equation, and then we solve that equation trying to see when it's going to equal 20 billion. All right. All right, so another important point for quadratic functions is finding this maximum or minimum value, okay? So when A is positive, these things are going to open up, and then I'm going to have a minimum, okay? When A is negative, it's going to open down. And then what I'm going to have at the vertex, I'm going to have a maximum. Okay? All right, you may remember finding a formula for a vertex from a previous math class. Okay? We're not going to go into it. Okay? To find the vertex, x, the x coordinate is always negative b over 2a. Okay? So this tells us that the x value is negative b over 2 times a, and that the y value of the vertex can be found by what? Plugging in x, once you find it, into f of x, and that gives you the y value. Okay? So if you're asked to find a minimum or a maximum, that's how we're going to do it. Okay, so let me put all of this stuff together here. So this is basically section 4.4. Okay, we have this data, okay, and they've given me a plot for it. So I certainly look at that plot and determine that that is not linear, right? If I'm trying to put a line to this, I'm going to do that. It's not linear. It certainly looks quadratic, okay? So let me find the line of best fit. So I'm going to go into my calculator, stat, edit. Looks like L1 is going to be 10, 20, 30, 40, 50, and 60. L2 is going to be 57, 86.2, 99.4, 86.2, 73.6, and 53.2. Okay? Then I'm going to go stat, calculate quadratic regression, because this is not linear. And I'm getting y equals negative 0.063 x squared plus 4.19x plus 24.4. So that's the equation that I get when I do my quadratic regression. So A is negative. So what does that tell me? A is negative. So it opens down. So I'm going to have a maximum at the vertex. Okay? All right. So how do I find the vertex? X equals the opposite of B over 2A. So what is the opposite of B? Negative 4.19 divided by, I'm going to put it in parentheses, 2 times A, which is negative 0.063. So hopefully you can see that. It's not too much of a glare. So I'm getting X is 33.25. Okay. Now here's what I'm going to do. I'm just going to store this value as X. Okay, so now X on my calculator is that, and then I'm just going to type in this function, negative 0.063 x squared plus 4.19x plus 24.4. And I'm getting y equals 94.07, rounding to 2 decimal places. Okay. So again, what I did there, once I found X, I hit this little store key. So now I could store that as X if I wanted to. Okay. And that really helps me evaluate functions. So you might want to try that. All right, so which part of the vertex, the X or the Y, is the maximum? My maximum is 94.07, and we say at 33.25. So it's the Y value that's the maximum. Okay, the X value tells me when it happens. And let's see, this is going to be price. So X is price, so that's $33.25. And this is also dollars because this is my profit. So this would be my maximum profit. Okay? So that's a little bit in using quadratic regression. We find an equation. I can find the vertex anytime by using this X equals negative B over 2A. Okay? So hopefully that works with section 4.4. Good luck.